There was lots of questions last time, so I encourage you to just ask me questions as I go, while I'm on the slide. So you don't have to flip back to 100 slides and answer your question. Okay, so today I'm going to go over just some recent developments. In particular, this iron chloride compound, which has received a lot of attention since roughly December last year. And much more recently, these platinum-doped calcium compounds, which are just the last 3 weeks or so, have appeared from several groups, actually. Okay, and then I'm going to cover some rare earth doping of calcium iron 2 arsenic 2, which is from our own group. And there's been also some recent reports from a couple other groups with the same results. And I don't think I'll have time to go through this, but if I do, I'll get to that as well. Okay, so potassium X iron 2 selenium 2. This is the first report here, November 2010. So this nominally has the same so-called 1-2-2 structure, which is the thorium chromium 2 silicon 2 structure, as the iron arsenide compounds that I talked about yesterday. So, for instance, barium iron 2 arsenic 2. So instead of barium here, you have potassium, and instead of arsenic, you have selenium. So if you just do some simple valence counting here, you can see that there's something not quite right? So barium iron 2 arsenic 2 would have barium 2 plus, iron 2 plus, and arsenic 3 minus. So you get some balance there. Here you have potassium, and selenium is 2 minus. So something isn't right, and that's why you have an X here. And in fact, it turns out this 2 also isn't quite 2. So before I get into that, though, there's some very peculiar properties of this compound. In particular, there's good evidence, and I'll show it, of magnetic order that onsets at almost 600 Kelvin. Okay, and that magnetic order has quite a large moment. Actually, it's much larger than the staggered moments seen in all the other iron-based superconducting compounds. And it has a superconducting transition of 30 Kelvin. So this is quite a unique material. Now, you can see in this slide here, this is sort of just a summary. As you sort of change the chemistry of this compound, you can get everything from this is what I would call insulating behavior. This is a log scale in resistivity versus some weird downturn, but very relatively low resistivity in a superconducting transition. So, in general, this material is very sensitive to the chemistry. So we'll go into that a little bit more. Okay, so before that, as I said, there's some imbalance in the charge counting here, the valence counting, and it looks like this is accommodated by introducing some vacancies in the iron site, as well as the potassium site. So K, instead of potassium being 1, it's close to 1 or less than 1 somewhat, 0.8, 0.9. But the iron, instead of being 2 here, is actually closer to 1.6. So what happens is you have this unit cell, which is a 1-2-2 unit cell, but now you introduce some iron vacancies. And the interesting thing is that these vacancies can order. So the vacancies order in this structure, and that gives you a superstructure like this, and it enhances the unit cell, and you get this so-called root 5 by root 5 unit cell. And it gives you different symmetry. So this is some neutron scattering data, and I believe this is structural. Yeah, these are structural peaks. And you can see that there's some different behaviors. Now this is one of the particular compounds, just as an example, to show you that there's some structural ordering that changes as you cool this thing down. And here's one of the nicer phase diagrams that has appeared, talking about mostly structure, but also the physical properties. So you can see that this is a function of X, which is the potassium content, going from 1 downward. You can see that there's generally a structural transition up here that coincides with this magnetic ordering. And there can also be some intermediate structural transitions here from between these different vacancy ordered symmetries. this side, it seems, at least in this study, that the superconducting compounds do not have this intermediate structural fitting. Very strange. Okay, so regarding the magnetic order, the other peculiar thing about the magnetic order, other than it being 3 Bohr magnetons, staggered moment, is that the moments are aligned along the z-axis. So this is much different than all the other iron arsenic materials and iron chalcogenide materials, which have staggered moments, Q vectors that are in the plane predominantly. So more or less commensurate and looking like nested vectors with the Fermi surface. So here you have c-axis moments.
Can I ask a question here?
Yeah.
So how well do you know that that is 2 minus x over 2 on iron?
Oh yeah, I don't know. That's what they claim.
Okay.
But I was told the day before I left for here that there's some evidence for the iron valence actually adjusting. So different from 2 plus. And so that, that's going to affect this kind of counting. But, this is, as far as I know, this is not reported yet. Okay, so you have this, large moment C-axis antiferromagnetism. It's, as far as we can tell, it's coexistent with the superconducting order.
So what you mean is like diluted amount there? Because you say you remove the good ruckus.
I'll get to that, yeah. Regarding the vacancies, yeah, I don't know. This is a good question. But there is some preliminary evidence for some phase separation. Whether that's due to the vacancies, I'm not sure. Okay, so regarding the band structure, another peculiar thing about this is that this is, I guess, considered extremely electron doped. So in other words, or at least the calculations, so there's a nice paper by Mazin considering all the different possible superconducting order parameter symmetries. The calculations show that there's no hole pocket, so the gamma point is empty here. And then here's, I just picked some from 3 groups. There's some ARPES data. I have more to say about ARPES in a second, but at least in this case, there's no evidence of a hole pocket here. There's no evidence of a hole pocket here. It's just electron pockets. Here's just some faint signature, but it's very weak. So this is unique because here we have a 30 Kelvin superconductor. We have no hole pocket, and we have large moment antiferromagnetism. So it's in a sense thrown a wrench into the understanding of the iron arsenides to some degree, at least at the level where people think that there's some nesting vector between the hole and electron pockets that plays some important role in the pairing mechanism. Okay. So just to show you a few other details on experimental results. If you apply pressure to this superconductor, Tc goes down. Now again, one disclaimer is that I think a lot of these things may be very dependent on the chemistry. Oh, and I forgot one thing. If I go back to, for instance, this behavior here, looking at the different structural and magnetic transitions as a function of temperature, I've also been told that depending on the thermal history of the sample, this can also change. Okay, so not only the chemistry, but the thermal, so whether you quench this, whether you heat it up slowly, you anneal the sample, that can also affect the vacancy order, as you might expect. You have ordered vacancies. You can imagine if you heat it up and you quench it down really quickly, the vacancies may be disordered. And I'm still not clear as to how that relates with TC and so on, whether the superconductivity appears or not. If I remember correctly, I think the vacancies have to be ordered in order to see superconductivity.
No, it's the other way around.
It's the other way around.
At least that's the claim. Yeah.
No,
That's the claim.
TC doesn't change.
TC does
I
not
said it's
change.
the claim
TC
from one group. I know
Yeah,
that
so
there's
there was-
controversy about this. Yeah.
Archive paper, STM archive paper, posted a couple days ago.
Shows which way, that it has to be ordered for superconductor?
Disorder.
Disordered, yeah. right.
Disordered, yes.
Which group is
Right,
that?
Sequential.
Okay.
Okay, yeah.
I would do have a question on the on that ARPIS data. So far, what's seen in literature is that those compounds are very hard to grow very clean. So there's quite big disorder also because it's probably not 1-2. How wouldn't that affect the ARPIS, since this is very surface sensitive, and might that be misleading to the band structure and what they actually see?
I'll get to that. Yes, but it is 1-2, or at least it has. It has a 1-2 symmetry, but you know.
Yeah, but it's not
depending on the
stoichiometric.
vacancies.
It's probably not stoichiometric what we see from X-ray.
Yeah, stoichiometry is not. Yeah, so there's vacancies, potassium. It's very messy. Yes.
No,
The
but
crystal
the
symmetry
issue is are the ions which are present in the 1-2 structure or not? There are certainly vacancies.
I'm sorry, say again. The irons.
I mean, do the ions that are present form a 1-2 structure?
Yeah.
I think that's
Yeah, absolutely.
at least, although there's inhomogeneity, there's some. Yeah.
Of course, one of the very surprising aspects of this one, as you know very well, is that you have a very large magnetic ordering temperature and also a very large ordered moment, which at least would kind of irritate some. So, is it? Let me put it this way: what is the evidence for bulk superconductivity in those systems?
There is pretty good evidence. So there's complete diamagnetism.
There's complete diamagnetism, and we know it is 100% of the sample is diamagnetic.
Yeah. I mean, as far as you can judge.
Because these are very hard to make judgments, as far as I know.
Yeah. No, you're right. So here's diamagnetism.
And what
It's
exactly?
you know,
being
the
done?
estimate says that it's 100%. Okay. That could mean that this you know the surface is superconducting. But there's also a specific heat evidence for the transition. So there's evidence for bulk superconductivity for sure.
So it couldn't be 10% and mistaken.
I'll get to that.
Okay, good.
Okay. Okay, a few other things. There's been several substitution studies. As far as I know, everything suppresses TC in some way. So here's cobalt, for instance, and cobalt concentration. This suppresses TC. I did see a report of manganese substitution, which does not affect TC. It kind of stays constant. But then I think you have to consider how much scattering is going on. So if you actually normalize the scattering rate, it may all look the same in the sense that you're introducing more disorder.
How TM sensitive to?
I don't know. I don't know that has been
Because
measured.
it seems to be so flat, but there.
Yeah, yeah. At least for potassium content, it's insensitive.
Common concentration here is electron doping or proton doping?
This is well. This is balanced in some way, but this is a good question. So there's a nice study here on sulfur substitution, and you can go all the way to potassium iron 2 sulfur 2, which is here. And this looks like an insulator. So there's some indication of a phase diagram here. It goes from insulating to superconducting to metallic. Okay, these are all very recent results. Yep.
So for the parent compound iron 79, there's already some debate about is there vacancies over there and iron in the parent compound and which causes the disorder and makes the emerge. So
Which compound are you talking
iron
about?
79.
But not 1,2,2. You mean iron 1, selenium 1?
Yeah, something like that.
That's a completely different compound.
So it's kind of become 1,2,2 system.
Because iron selenide is basically these layers without these. And in that case, the iron, there is interstitial iron that I think sits here, and that the amount of that varies. You can never get it to iron 1, selenium 1. It's always iron 1 plus a few percent. So that interstitial iron does play a role in the magnetic properties. Yeah. But that's there's no iron vacancies in that system. properties did I include? Okay, yeah, there's heat capacity here. Okay. So first of all, HC2 again is quite large, and this is a similar anisotropy as to the iron arsenide materials. It starts out as large, and then it looks like it's going to come back towards 1 at low temperature. There is amazingly ARPA's data on the gap already, and it looks isotropic. Okay. The specific heat data here shows the residual gamma as a function of field. I'm not sure what temperature this is, I don't remember, but it does not look nodal, at least in the sense that you would expect some square root behavior. Okay, so there's error bars on there and so on, but it looks kind of activated. This is quite low field. Okay, what else? There's a neutron resonance that's been observed already. And this, I don't know about the numbers, but this looks qualitatively similar to the other data I showed yesterday in terms of the appearance of the neutron resonance below TC. I'm not sure about the energy of it related to TC. Okay, so there's some other properties. There's singlet pairing. There's a night shift data here. It shows singlet pairing. And in normal state, there's Kringa behavior, so it doesn't look like there's any effective spin fluctuations, at least in this experiment.
Isn't there also an NMR report of T cubed in the superconducting state? I've forgotten which case it was.
Yeah, I think maybe from China?
Yeah.
Yeah.
Okay.
Yes. Okay, so back to ARPA's data. There's a nice paper here which talks about where you do the ARPA's measurement on sample, and they get different results.
Ah.
So, okay, so this addresses the question of disorder and so on, and how do you interpret ARPA's data. But there's a very nice result here in that if you look at different parts of the sample, some look like a semiconductor, there's a gap here, some look like a superconductor.
So ARPA's is made by one frequency or is it like a daily reset frequency?
Well, I'm not sure what you mean by the frequency.
Well,
The energy?
Yeah.
Well, it looks at different energies in different data, so it maps them. At least in this, this is a small energy range. Is that your question?
Jean-Pierre, why is the left panel labeled superconducting? Just because their state's at the Fermi level?
I didn't have time to read the paper.
Ah, okay. Nature of the field, huh?
This is, this is a school, right? So this is the importance of taking, you get to my age, I'm young, but you don't read papers anymore, you just look at figures, right? Figures are mucho.
Don't tell the students that.
Okay. Well, actually, here is some. Okay, this is some evidence here. You can see that there's a gap.
What did you say?
Okay, and this is angle integrated, I think. Again, there's a big gap here, and this is a nice sharp feature in the Fermi level. Gap opens below TC. So this is very nice. Okay, so the conclusion here is that there is some phase separation, at least at the surface, right?
Yeah. I mean, it could be just crap on the surface, right?
Of course.
Dust mites or something.
Of course. So the other pieces of evidence, okay, so I value these a little bit more. There is, Haidu Wen's group has looked at magnetization in great detail, and to summarize, basically they see behavior that's consistent with a percolative superconducting state. Okay, that's one piece. And then another experiment is Mossbauer, where the conclusion is that the magnetic fraction of iron is about 85%, which means it's very briefly that you have a superconductor and there's only parts of the sample, parts of the volume that are superconducting. you need enough to have a full percolative path to make it look like a bulk superconductor.
But then that is completely different from what we said from the diameter. You were telling us that diameter is not
Yeah, but you know, I think it's very, as you know, it's very easy to see 100% diamagnetism in a non-100% superconductor. The easiest case is coat a piece of gold with lead.
Then you do a real measurement.
Yeah. Okay, so and of course the screening fractions in diamagnetic measurements are estimates based on how well you know the volume and so on. Okay, so this is a very interesting result. The Mossbauer shows 15% of the iron is not ordered. So again, this is other evidence for some kind of phase separation. And this is my current understanding as far as we know. This is sort of the latest results.
But that's not in the superconducting state, is it? That's all just in the magnetic order state?
Yes. So this might resolve the fact that you have a large moment, 500 or 600 Kelvin antiferromagnet and a 30 Kelvin superconductor.
Just the remaining stuff.
You take one, you take the other, you put it in a blender, mix it up really well.
Not too well.
Not too well, right? Okay? Yeah.
This STM paper clearly shows atomic resolution on the two different regions, the superconducting and the non-superconducting. It's just listed a couple days ago by the Chico. So it clearly shows the atomic resolution and phase separation. It doesn't suffer from the possible dust mite problem because you can see the atomic resolution in both regions. So yeah, I'm just supporting with more locally resolved evidence.
Good, okay. Yeah, I haven't seen the STM. Is there posted STM?
It posted in the archive a couple days ago.
Oh, wow.
Yeah.
I haven't got to that.
Hey, you're supposed to be reviewing the field.
Well, if my hotel internet connection is, stable in any way, then I would do that. I tried to load Netflix last night. Okay, so any other questions about that? I'm going to go on to the next. Okay, so this is an even more recent result. So here's the compound. It's a mess, okay, but I'll show you a better crystal structure in a second. It's calcium, iron 2, arsenic 2 in some fashion with some platinum arsenic intermediary layers, as well as some platinum and iron substitution, I think. Okay, there's 3 papers at least that have shown up showing, again, some Miser screening of the superconducting state and some scattering results. Okay, so here's a nice picture by, this is Nini and Now Cow's group. You can see the two, so there's so-called, they call it the 10-4-8 and the 10-3-8 structure. Very similar. So again, here's the iron arsenic layer, and then here's the calcium, and then you have, let's see, you have an arsenic layer here, and then you have some platinum substitution in there. And then the difference between these two is that you can see that this is inverted here. This layer, these layers are the same. So essentially the unit cell is cut in half in one of these two. Okay, there is some ordering, I believe, to the substitution of the platinum. And that's shown here. Okay, and then there's some analogies to some scutterodite type intermediary layers. So you can think of this sort of as a scutterodite layer inserted into the iron arsenic tetrahedral layers. Okay. Yeah, not much data to show. Here's resistivity. This is from the Japanese group, and they claim that there's some different behavior in the two types of crystal structures. Not quite resolved yet if this is true or not. There's some weird transition here, but there's definitely superconductivity there. These guys report up to about 30K. There's an abstract that claims up to 38 Kelvin. This is I believe this is Geidel's group. And they show up to 35 Kelvin on onset temperature. Okay, and then there's some decent refinements of structural data that indicate this structure is correct. Okay, a few more data sets. HC2 in, let's see. This is a roughly 10 Kelvin superconductor. HC2 here is 10 Tesla, maybe 30 Tesla or something like that. In this case, it's a little higher. TC is a little higher here. Okay, so similar properties to the iron arsenides, more or less. Okay, questions about that? That's all I can find, except for the last 3 days.
While watching Netflix?
Okay, so finally, how much time do we have?
Well, 10 minutes left.
Okay, good. So this part, I'm going to focus on our own work on this material, which is calcium iron 2 arsenic 2 substituted with rare earth. So the question came up yesterday about electron doping in the alkali earth site instead of in the iron site. And so this is an example of doing that. So you're putting in rare earth 3+ into calcium 2+. And so that's why we got interested in this study. There was one report of a similar compound by Hosanno's group maybe 6 months ago on the strontium system. So they put lanthanum into strontium-122, and they get a 20 Kelvin superconductor there. And the synthesis there is difficult because they have to do synthesis under pressure. Here, this is all ambient pressure synthesis. Okay, so we reported this recently, and then there's a couple other papers by the Chinese group and by the Paul Chu's group reporting similar results. Okay, so here's the group. I'll show this later, but these are my students. This is work with, in particular, Peter Zavali's a crystallographer at Maryland, very good, and Jeff Lynn at NIST, who actually did all the neutron scatter experiments himself. So, commend him for that. Okay, here's some background. Going a little further from yesterday, this particular compound, calcium iron 2 arsenic 2, is a parent compound. It has a nail temperature of 160, 170 Kelvin, just like the other 122s. And you can dope this in a transition metal site, just like it was shown yesterday, to induce some superconductivity. You can apply pressure in the same way, but one thing happens that's very different than the other compounds. When you apply pressure to this material, you run into this very severe structural transition. So that's shown up here. Now this is C-axis unit cell and A-axis unit cell versus pressure. This is at 50 Kelvin. Just pay attention to the C-axis here. This goes from 11.5 angstroms at about 0.3 gigapascals, which for you guys that don't know is a quite small pressure, 3 kilobar. It's very easily obtainable. And this jumps by almost an angstrom. So the unit cell shrinks by 10% on the C-axis. Okay, A-axis actually goes up a little bit by maybe 1%. It's a much smaller change. The volume actually changes. The internal coordinates and so on change, as you might expect for such a drastic phase transition. So what happens is you suppress this magnetic order and then suddenly you run into this collapse transition. Okay, I'll get to this later. We have some evidence now that directly indicates that this collapse is simply caused by the fact that the interlayer arsenic atoms decide to bond once they're close enough. So the p orbitals overlap and they hybridize in some way, and they form a bond that's preferred once these guys are close enough. Okay, I'll get back to that. One of the consequences of measuring a sample that undergoes a 10% change along one direction under pressure is that when you do this measurement in a pressure medium that's not helium, you end up with some very strong straining on the crystal. So you imagine that you have some liquid pressure medium that becomes a solid at low temperature, and you have a sample in there, and you're cooling the pressure cell down, and then suddenly this sample shrinks by 10%, well, you have a void in there and you have a very strong anisotropic strain on the crystal. So these were the first experiments that were done because they're the easiest ones to do. And superconductivity was reported once you suppress this thing here. Later experiments showed that when you did this under a truly hydrostatic condition with helium gas, there's no superconductivity here. So this is an anomaly. It's not understood as far as I understand. But the strain-induced superconductivity is another question altogether. I'd be happy to talk to anyone about that later. In any case, you have to be very careful about doing experiments under pressure in a system like this. So we decided to do rare earth substitution to see if we can induce this collapse with ambient pressure conditions, so we can do all these experiments without this problem. So we basically take the light rare earths, which are a good size match for calcium, and try to put them in. Okay, so it turns out that calcium, if you just take the ionic radius, is somewhere between presbyterian and neodymium. This is just the elemental ionic radius for an A-coordinate condition. In reality, it turns out to be more like somewhere over here with respect to these light rare earths. But it's a very close match, so this is why we can actually grow these crystals. Okay, so here's some, these are results on all single crystals. This is the concentration of rare earth we start with, and this is what we get, what we measure. And you can see that for lanthanum, for instance, we get a pretty good linear relationship up to some higher concentration, and we kind of run out of steam, so you can't put more lanthanum in. And then as we make the rare earth smaller, we can put less and less. So by the time we get to neodymium, we can only put about less than 10%. And the more we try to put in, it just doesn't fit. At least with just this ambient pressure growth. Okay, and then if we characterize the unit cell parameters as a function of rare earth concentration here. This is A-axis. There's some scatter here, but more or less the A-axis increases with all the rare earths we put in. It doesn't matter about their size. The C-axis, however, is very strongly dependent on the size. So lanthanum actually very minimally suppresses C-axis. It's almost constant. Whereas the other extreme is neodymium strongly suppresses C-axis. So this is what we want. We want to put in small rare earths and cause this collapse to occur with ambient pressure. Okay, so here's some neutron scattering data. Sorry, show this first. This is with lanthanum substitution, which, as I said, does not cause a shrinkage of the C-axis. And this is A-axis and C-axis versus temperature. Okay, nothing funny happens. But when we put presbyterian in, you see that there's this structural transition. And again, this is roughly 10% or so of the unit cell. So this behavior looks very much like calcium 122 under pressure. And then this is cooling on temperature. If we increase on temperature, it's the same thing, but it's quite hysteretic. This is 40 Kelvin, this is 60 Kelvin. So there's a big hysteresis. And these are ambient pressure measurements. Okay, so to summarize, this is the C-axis data for several samples as a function of temperature. This is the calcium undoped compound under pressure, just to compare. So you can see right away that this collapse here is quantitatively the same, more or less, as these rare earth doped guys under ambient conditions. So here we have a suppression of the C-axis due to thermal expansion, and then a collapse in these guys. Whereas if we put lanthanum and even cerium here, there's no collapse under the lowest temperatures. Here's a very lightly doped presbyterian sample, just to show you that when you start with an undoped compound, you put a little bit in, you suppress this magnetic transition as well. Sorry, this is a structural transition, but it's coincident with the magnetic transition. Okay. Here's a mess of data, but I just want to focus on two things. First of all, the thermal expansion that we see here, even in the samples that do not undergo the collapse, is huge. It's actually 130 × 10⁻⁶. So this is of the largest expansion I can find in any reference books. So that's quite neat. The other thing is we've done some X-ray scattering. Single crystal X-ray scattering is a function of temperature. And this is the interlayer arsenic-arsenic separation here. So I'll blow that up in the next slide here. You can see that basically the samples that undergo this collapse hit this 3 angstrom line. So this is basically the magic number. Once these arsenic atoms are 3 angstroms apart, they decide to bond, and the collapse occurs. If that doesn't get to 3 angstroms, like in this case here, you do not undergo a collapse, but they are still, they're close to collapsing. It's like an anharmonic effect. They're pulling together, the unit cell is holding them apart, and so that's what I think causes the strong thermal expansion. Yeah.
So in the standard 1 to 2s, the barium, the strontium, etc., they're much larger than 3 angstroms apart?
Yeah.
Thanks.
Okay, and just to confirm this, if we take one of these samples, this is cerium, it's very close. We go to low temperature and we apply, this is now half a kilobar, so that's 10 times lower pressure than the calcium 122 pressure that's needed to induce the collapse. And here's the C-axis, it drops. So this is confirmation, 2 minutes. This is confirmation that you really need to just hit this 3 angstrom line to cause this collapse. Okay, so going on to some physical properties to finish up. This is a lanthanum doped series. This is a praseodymium doped series. This is magnetic susceptibility to temperature. You can see the undoped compound undergoes this well-known structural and magnetic transition. As you put lanthanum in, it's suppressed, and this is more or less featureless. There's a bit of a tail here, but it's not very interesting. The praseodymium sample, on the other hand, undergoes this very strong collapse, and that's indicated by these hysteretic drops in susceptibility that first appear here, and then they march up a little bit in temperature as you put more praseodymium. Here's the resistivity, same series, lanthanum and praseodymium. Suppress the magnetic order, and here's this large upturn that I was referring to yesterday that persists. So that's quite different than the potassium substitution. And then at some concentration, you get superconductivity. So that's quite interesting. And the really weird thing is that with praseodymium, we also see superconductivity. And that's in the presence of this collapse. So this is the most anomalous result here. And there's some caveats to this. First of all, to summarize some resistivity data, and here you can see a neodymium sample that very clearly shows the hysteretic behavior, and then it shows the superconducting transition. So the caveat is that the Meissner screening fraction we see here is very small. All the samples we measured, the screening fraction is small. We don't know why. We don't see good evidence of bulk superconductivity. Nevertheless, it's always showing superconductivity here. Okay, so just to wrap up, here's a phase diagram. Now what we've done is, the black curve here is just showing the calcium undoped compound under pressure. So here's temperature, pressure, and here's the suppression of the magnetic order, and then it hits the collapse here. Here's the collapse transition. Now as you put in rare earth, depending on the rare earth, like I said, you induce some chemical pressure. So the other extreme is lanthanum, which does not induce any C-axis change. So I call that zero pressure. And you just suppress the magnetic order continuously, and then you have some superconductivity here. We don't see coexistence evidence. And then at intermediate rares like cerium, praseodymium, neodymium, you're doing something in between. So we're kind of able to span this doping pressure phase space more or less continuously by choosing the rare earth. Okay, so I'm out of time. I can show you some other results from other groups if you ask a question. But thank you very much.
So I think I missed your motivation for doing this. It's very interesting, of course, and it's great, fascinating results. But the initial experiments on the collapse on the calcium material showed that the superconductivity was there only in the stressed phase, right? And now you're trying to essentially, I would imagine, reproduce some kind of analog of the hydrostatic pressure,
Yeah.
right? Uniform chemical pressure.
Yeah.
And that would be no superconductivity.
So,
Yet you get 47 Kelvin, so what's
so
the
this is
connection?
where I said the strain-induced superconductivity, I believe, is somewhat different. First of all, the strain-induced superconductivity in calcium-122 is maximum 10 Kelvin. Never seen above that temperature.
Right.
There's some evidence for that in the other 122 materials, up to 20 Kelvin. The superconductivity we see here is, approaching 50 Kelvin, and I believe it's of a different nature. Now, how do you have one and not the other? I'm not sure, but I can say in some samples. In some samples, we actually see evidence of, you see this here, there's some indication of a small transition here, even 3 actually. There's something at 40, something at 20, and something at 10. So, while I don't want to say that there's 3 superconducting transitions in one sample, there's evidence of this 10K phase around,
Right.
and that's why I think it's due to some strain. So we're in the process of doing annealing and all these kinds of studies to see how we can, isolate one or the other. But I think that they're different phases. So in essence, I think the calcium 122, I think you have to dope it in order to get this higher TC phase. I think that's clear. But actually, our real motivation was to electron dope outside of the iron site. That's really why we tried to do it.
Do you have any idea why that would give you this, what amounts to an extraordinarily high TC for the 122 family, modulo your caveats?
Well, I think it's the same reason that the alkali metal substitution gives you up to 40K. So it's just less disorder.
Okay, so that you buy that kind of picture. Okay.
So what's the statement now regarding superconductivity? Only occurs in the collapsed phase, or of praseodymium, let's say?
From what we observe, it occurs all here. So in the rare earth dope samples that show the collapse, praseodymium, neodymium, and also the ones that don't. But the caveat that maybe it's somewhat foreign phase, but to me it's very hard to believe that you have a crystal that undergoes such a dramatic change in structure, and you have enough left over of the some non-collapsed phase to have this superconductivity. But it's possible, yes.
But even the ones which collapse only occurs in the collapsed phase.
The collapse transition is always above. Yeah, it's always above the superconducting transition. Is that what you mean? There's a question here. She asked first.
Simple question. Is there any 122 system compound which is paglione has been reported instead of peptide beside this potassium iron?
No.
That is the only one.
Well, there's the salt. I talked about the sulfur. There's a sulfide. That's all I know of.
One possible interpretation of the data that you mentioned, when inhomogeneous pressure medium gave rise to superconductivity while homogeneous didn't, was that you would have signatures of a non-collapsed but tetragonal phase in the sample that would then, because there's no magnetism, would be superconducting.
Yeah.
Just as a metastable state that might filamentary superconduct. This seems to be inconsistent, this naive interpretation with your data of these much higher TCs. Is that so, or do you see it differently?
So you're talking about the existence of superconductivity in the collapse phase?
Yes.
Yeah. So while this is a poor representation of the data, I can show you actual intensity curves, but there's really small, there's really small intensity of this phase here, and so same thing here. So, well, you would expect it to be here, right? So, well, it's, you know, we can't say that it's less than, well, we can say it's less than 5% or something like that, which may be enough, but.
Because, I mean, at first glance one might think that the collapsed phase is what might be referred to as a vegetable,
Yeah.
magnetically.
Right.
Yet you are saying this may be the most interesting phase because it gives rise to the highest DCs, at least as far as superconductivity.
Well, so that's not true.
Okay.
Because, let's see, while our samples show up to 30, 35 Kelvin with lanthanum.
Yeah.
Let's see. The Chinese group is showing up to, here it is, 42 Kelvin in lanthanum, so similar TCs.
Yeah. Okay.
So is that strain-induced superconductivity bulk or on the surface?
Actually, there's evidence for bulk superconductivity. So there's NMR data, and there's even specific heat under pressure, which seems to show that 10 Kelvin phase has some bulk behavior, or bulk properties.
From NMR, can you deduce what kind of pairing symmetry?
Oh, yeah, in theory you can. But this is NMR under pressure, so it's, yeah. I mean, what you mean, singlet or triplet, or?
Yeah.
I'm not aware that they,
And
well, they must have shown some night shift, but I don't know if they,
how is the temperature dependence?
I don't remember off the top of my head.
Okay, so there's this correlation between the iron arsenide bond angle that we've seen earlier in the week. I was just wondering, I don't know if this is a relevant question or not, but how does this structural transition, this collapse, how does that fit into that picture? So could it be the same effect that after reorganizing itself it is?
Yeah, so here's the bond angle as a function of temperature.
Okay, yeah.
And
Okay, so after the collapse.
so calcium starts around close to ideal, 110,
Yeah.
109.5 is ideal. And it goes away, and the guys that undergo the collapse go really far away.
Okay, but they're not the ones with the highest TCs, is that?
They all show fairly high TC.
Yeah, okay.
Yeah. And you know, you can understand that by just you're just squashing this layer so that the angles display out.
So I have the feeling that if I were a student watching all of these presentations, that I would say this is not a field I want to go into, because I see a whole zoo of materials and they all seem to behave in different ways, and there's no one or two variables which seem to control their behavior. At least we haven't found them yet. What's your perspective on this? Is it just everything in details, or is there something universal that we're going to be able to extract?
Well, that's why I tried to emphasize the phase diagrams. I think this is an important clue. I mean, you know, even here you have all this weird behavior. But at the end of the day, well, here's an example. You have a phase diagram where you're suppressing magnetism and you're getting superconductivity. I mean, very bluntly, I think that's common to almost all these materials, except maybe the iron solid. But that's a very strange. Okay, once we get the chemistry under control of that system, we know exactly what's happening with this ordering and all this stuff. Those are details, I think, that are affecting the interpretation. Regarding the gap structure and so on, I think, again, I try to emphasize that the symmetry, the gap symmetry seems to be consistent. As far as the data that we have tells us. The structure varies, and that's probably kind of detailed as you can explain better than I will. So I think these are the key things. You know, anyone else wants to add to that?
I have a question about these. Well, when you collapse it, you think that the arsenides bond together. Do you have any sign of less anisotropy in the, let's say, critical field, to basically state that this is like the phase that's actually superconducting and showing less anisotropy which basically would mean, yeah, it is
Right, no,
three-dimensional.
we don't. So if we introduce Presenium and we obtain a nice bulk, well-behaved superconductor here, I would be touring the world, with this data because the fact of the matter is that we have good evidence that these interlayer arsenic atoms bond, and that's dramatically changing the electronic structure. Both known by calculations and also by experiment, by comparing other 1,2,2 structures like phosphides that we know are collapsed in a sense, and they show a quite different. In fact, the whole pocket disappears in the middle, in the channel point. So if I was able to conclusively say that this superconducting state is robust, it's there in the collapse phase, then we could have some very strong conclusions about what's the nature of superconductivity, because if there's no magnetism here, then we can say something about the pairing mechanism. But I can't say that at this point.
A very basic question, a little bit in his direction and what you said as answer. I only know a few of these compounds, a little bit, and everyone always talks of the antiferromagnetic phase. Is it always the same order, or is there different orders in the antiferromagnetic phase?
In this phase here, so
Just in general over all the pnictides, or iron-based superconductors.
iron arsenides, yes. It's always commensurate.
described
It's always commensurate. AF order. There may be a bit of a c-axis component to the q vector in some cases, but it's always half-half. Which is why there's a lot of discussion about nesting between the hole and electron pockets. The iron selenides show a different, so the binary iron 1 selenium 1 show a different magnetic order, which is actually it's a half zero, I believe, and it's the triangular unit cell. So it's slightly different. And that phase diagram is a little bit different.
And is there in some, so in the same magnetic ordering, one expects the same behavior with coexistence or phase separation, or?
As one expected, I don't know the expectation. So you mean if there's a...
I mean, depending on the underlying magnetic structure,
Yeah.
it is easier or harder to have certain gap symmetries coexisting. And so...
Yeah, so the two cases that I'll answer experimentally. The two cases that I showed of phase diagrams which show coexistence and don't have the same ordering structure, magnetic ordering structure.
Can I comment on that?
Of course.
I mean, I think from the point of view of most of the theories of superconductivity which rely on spin fluctuations, what's important is not necessarily the ordering wave vector, but the wave vector of the inelastic fluctuations. And in most cases, they're the same. But in the chalcogenide examples that Jean-Pierre mentioned, they're actually not. The double stripe phase in the iron, is it tellurium, I think, or whatever, is which one? Iron telluride, yeah. That's a different ordering wave vector than the usual one. But then if you look at the inelastic fluctuations, they're back in the usual place again.
That's right. That's a good point. And the resonance. That's right.
And in the new system, in the iron selenide, they're apparently slightly different.
Okay.
But everything else is different, so why shouldn't that be different?
You mean the inelastic fluctuations in the superconductors?
Well, in the materials which are superconducting. Yeah.
So the binary iron selenide telluride 50/50 is a great case because there's the telluride orders at half zero, but the neutron resonance is observed at half
Right.
below TC.
In the two iron zones.
There's coexistence.
So I'm afraid we have to cut off the discussion here because lunch is waiting. So